So let's go back to look at this problem again. Again, we have this crane here, supported at point A with a pin, supported at point B with a rocker, and it's trying to carry the crate. A fixed crane has a mass, this time it has a mass, this self-weight, of 1,000 kilogram, and is used to lift a 2,400 kilogram crate, this one. It is held in place by a pin at point A, so they said that. Point A is a pin support with a wall. Also is supported with a rocker at point B, so point B is a rocker. So this is another kind of support. The center of gravity of the crane is located at point G. Point G is here. So equivalently, there is a concentrated load representing the self-weight of the whole rigid body going down. And that's what they said. The center of gravity of the crane is located at point G. In this chapter, if you ever see an irregular kind of rigid body, normally we tell you where the self-weight is located. However, for many problems in this chapter, if the geometry of the rigid body is very simple, you need to determine where the self-weight is supposed to be located. For example, if I gave you a circular shape rigid body, and then say, you need to consider self-weight of this circular rigid body, then you just need to put the force at the center, geometrical center of the rigid body, which is actually the center of the circle. Or sometimes we give you a square or give you a rectangular rigid body, then the self-weight should be located at the geometric center as well, the two diagonal cross points. Okay, so this is the problem statement. Now we need to calculate the components of supports, or called reactions, at point A and point B. So when you are designing this crane, trying to carry or lift this crate, we need to make sure we got enough support. How can we make sure we got enough support? Then we normally need to calculate the reactions, or it's called the support, at these points. We provide the pin and also the rocker. Okay, so in order to solve this problem, the first step, we need to plot the free body diagram. After we plot, or say create the free body diagram for the rigid body, or called the crane, then we can write down those Newton's first law equations. Essentially, for any two-dimensional problems, we have three equations for us to calculate those unknowns. Okay, number one, we need to plot the free body diagram of this one. So what we need to do next, first, is to identify the rigid body. So obviously this is an easy one. This is a rigid body. So this is the rigid body. So once we have a rigid body, we need to look at how this rigid body interact with outside world, right? So this rigid body is interacting with this crate through this cable. So that's why you need to cut this cable here, close enough to the rigid body. So when you cut this one, then this crate is equivalent to a force acting on this point going down. So that's the first force you need to plot on the rigid body. So this rigid body, we cut this cable, corresponding we gave this force. So this force is due to the crate. And from the problem statement, the crate is to have a self-weight of 2,400 kilograms. So 2,400 kilograms need to multiply with 9.81 to transfer kilogram into Newton. So that's why it end up with 23.5 kilonewton, okay, by multiplying 9.81. This is what we end up with. So this you can also call the self-weight due to the crate. Now, this rigid body has a self-weight. He said it has a mass of 1,000 kilograms located at point G. So in other words, you need to plot a force going down, because this is remotely interacting with the Earth using what we call the self-weight. So then 1,000 need to multiply with 9.81, you finally end up with 9.81 kilonewton. That's a self-weight of this crane. Okay? Let's go back to look at this again. This rigid body is also interacting with this wall, which is outside world, at point A. So then we cut point A. When we cut point A, we realize this is a pin. When we cut point A, which is a pin, then we need to plot two reactions. So these are the two reactions representing the pin support. You may say, how do I know at this pin the reaction force has to be to the right? How about to the left? or the vertical direction pin, how do I know the force is going up instead of going down? And nobody knows until you solve the problem. But it doesn't matter, you make assumption. So you assume at this point A, the pin support provides a horizontal reaction to the right. You assume this one. And finally, when you finish the calculation, you'll find out, in fact, this one is negative. Actually, later on we'll show you, right? In fact, you find out that AX equal to negative 107. What that means is the magnitude is still 107.1 kilonewton, but the direction, in fact, is to the left. But this only occurs after you finish the calculation. Before then, you have no idea. Then it's really up to you to make assumption. If you don't like to make assumption to have the horizontal force to the right, you can make assumption to have this horizontal force to the left. It's not a problem. Okay? Similarly, for this vertical support at point A, you don't know, then you just make assumption saying going up. If it's going down in reality, then you can find out there's something negative. So it doesn't matter when you make assumptions. Same thing at point B. Point B is another called a rocker support. If you have a rocker support, you cut this one, then correspondingly you need to give a horizontal force. At point B, there's no vertical force. The reason there's no vertical reaction is simply because this point is now the pin. It is a rocker. If you go back to look at the rocker, we only have this kind of support, right? There's no horizontal one. Okay, so with this, we successfully plot the free body diagram, what we call create the free body diagram. Once we have the free body diagram, then we need to move to step number 2, which is to write down the governing equations. So typically for three-dimensional problem, we can have 3 equations. Typically, we always calculate all the x component and add them together equals 0. So in other words, from this free body diagram, let's see what are those horizontal forces. You have this horizontal force called AX. You have this horizontal force called B. Then AX plus B, that's equal to 0. Because you don't have any other forces in the horizontal direction, right? So you call this is equation number 1. So this is the one representing all the x component together equals 0. And then you need to have another equation, the second equation, by collecting all y components and add them together equal to 0. So then go back to look at this picture. You consider all the y direction forces. You have AY, you have 9.81, you have 23.5. This is going up, that's why you have AY positive. This is going down, that's why you put a negative sign here. This is going down, you also put a negative sign here. So AY plus negative 9.81 plus negative 23.5, and add them all together, that's equal to 0. So this is called the second equation. So in addition to those force equations, we can also build a moment equation. The moment equation is something like this. So you need to first pick a point, and then you're going to calculate the moment due to all forces at that point and set equal to 0. So back to this specific problem we are dealing with, which point you want to choose? We can choose point B, we can choose point A, we can choose point G, or we can choose point H, for example. It's really up to us. Any point you pick, you write down those equations, combine with 2 existing equations, you can solve for 3 unknowns, which are B, AX, and AY. These are 3 unknowns, right? You have 3 equations, that's perfect. However, if you are picking point A, the equation becomes much easier. The reason is, at point A, there are 2 unknown forces at point A. So if you pick point A and you collect the moments of all forces at point A, you have no contribution from AX, you have no contribution from AY. And then from this one equation, you get point B reaction directly. Okay? So now, let's say we are going to pick point A, and we are going to collect all the moment of forces at point A equals 0. Okay? So first of all, what is the moment of force AX at point A? Well, that's going to be F times D. If you still remember chapter 3, we call the moment of a force about the point. For 2-dimensional problem, typically we use F times D. So D is a short distance from the point you want to calculate the moment of to the point, the shortest to the force line. So this is point A, and this force going through this with a shorter distance, that's equal to 0. So D equal to 0. So F times D, F is AX times D is 0. That's why this force has no contribution in terms of moment of this force at this own point. So that's why we don't need to worry about this AX. How about AY? Same thing. So what is the moment of AY at this point? That's going to be 0 because F times D. D equal to 0. D is a short distance from point A to the force line. This is a force line, and that's 0. So that's why you don't have AX term in here. You don't have AY term in here. But then, what is the moment of this force B acting on point A? So what is the moment of the force B acting on point A? So that's going to be F times D, right? So what is F? F is B, because the magnitude is called B. What's the D? D is a short distance from the point you want to calculate the moment, that's point A, to the force line. This is a force line, horizontal, this is a force line. What is the short distance from here to here? That's 1.5. So it's going to be B times 1.5. So this is the magnitude of the moment of this force at this point A. Then second, we need to determine is it clockwise or counterclockwise. So if you are fixing this point, then force B has the potential to rotate this rigid body at point A counterclockwise, right? So it's going to be counterclockwise, then it is a positive. So we will finally determine the direction, which is positive because of counterclockwise. So this altogether is the moment of this force B at point A. And then we're done with this first part. We have two more forces to consider. What is the moment of this force? What is the moment of this force acting on point A? So again, it's going to be F times D. What is F? That's a magnitude, 9.81. So you put 9.81 first. And then multiply the short distance, called D. What's the short distance from point A to this force line? So this time, this is a force line, right? So this is the force line. What's the short distance? That's this one. That's a 2 meter. So then put 2 meter here. So 9.81 times 2 meter. So this is the magnitude of the moment of this force at this point A. And then we need to determine the direction, which means it is clockwise or counterclockwise. So if you hold off this point, so this force has the potential to rotate this rigid body about this point clockwise. So if it's clockwise, then you finally put a negative sign in front of the magnitude. So altogether, this is the moment due to this force at this point A. Any questions? One more force, 23.5. What is the moment of this 23.5 at the point A? Same thing. The magnitude is 23.5 multiplied with D, the short distance from point A to the force line. This is the force line. The short distance is this. And that's going to be 2 plus 4. That's 6. So 23.5 times 6 is the magnitude of the moment due to this force. And then we need to consider direction. So you hold this point A. This force has a potential to rotate the rigid body again clockwise. If it's clockwise, you put a negative sign here. Now we have considered all the contribution from those forces in terms of moment. And then we add them together and the cycle 0. So now we have equation number 1, we have equation number 2, we have equation number 3. You combine those three equations, you can solve for these three unknowns, AX, AY, B. Many times, you need to look at each equation separately to see if it's going to be a simple equation. If you go back to look at this equation is called a simple equation. It's simply because this equation doesn't have AX or AY involved. This is an equation with only one unknown called the B involved. If that's the case, the problem becomes very simple. Just from this single equation, you calculate the reaction B directly without combining the other equations, because there's only one unknown involved in this equation. It doesn't mean the total number of unknowns is still 3, but from this equation, you can get one unknown solved directly. Okay, calculating this one, you get B equal to 107.1 and the kilonewton. And not only that, you find out this one you get a positive value. A positive value, that means in reality the direction you assume to the right is correct. In fact, it is to the right. Once you get B equal to something, you get back to plug in this equation. So then obviously AX plus B equals 0, B equals this one. You find out AX is equal to something with a negative sign. It's a negative 107.1. What that means is, number one, the reaction at point A in the horizontal reaction is 107.1 in terms of magnitude, but the direction is in reality to the left. Okay, so your conclusion is the reaction AX has the magnitude of 107, but the direction is to the left, in fact, because you have a negative sign. Whatever B you got, you plug into the second equation, you get AY. So AY equal to 33.3. So then this is the reaction in the vertical direction is positive, then in reality is consistent with what you assume is going up. Okay, so these are the three reactions we calculated based on this free body diagram. Another